kids. Okay, I am gonna do a little short instructional video about how the heck something moving straight can have angular momentum. So let's do a little thought experiment. So let's say that I have something like, okay, I don't know, it's a board, it's a rod or something like that, axis of rotation right in the middle of it, okay, and then I'm going to throw blobs of clay at it. So here's a blob of clay that I'm going to chuck at it. Here's a blob of clay that I'm going to chuck at it. Here's a blob of clay that I'm going to chuck at it. Here's a blob of clay that I'm going to chuck at it. And then here is also a blob of clay that I'm going to chuck at it. So I tried to do it. So we're going to pretend it's all the blobs of clay have the same mass. They're moving the same speed. I tried to make it so that this R is the same as that R. So just so you know, where this one hits here is R, this one hits here is going to be R. So I tried to make all that the same. If I label these with 1, 2, 3, 4, 5, I would like you, yes, you, to pause the video and see if you can figure out which of these things would cause the biggest angular impulse on said rotating bar thingy-ding here, okay? So pause it and figure it out. Did you pause it? Did you? Okay. Well, hopefully you did, and you thought about it, and you thought, but if you think about angular impulse is torque times time equals the change in angular momentum. Well, if you think about this, okay, object 2 is going to hit it straight on. Guess what? That would be no lever arm, so therefore there would be no torque. Object 5 is going to hit it this way. Well, if you look, remember the equation for torque is this. And this is the College Board's way of saying, hey, lever arm and force have to be perpendicular to one another. But if you look, lever arm, force, not perpendicular to one another. You know this because if you go pull on a door, it's not going to open like this, okay? Or you push on it, it's not going to open. So this and this, 2 and 5, would tie for the least angular momentum because it would be 0 angular momentum. So let's write that down. So 2 equals 5 because the angular impulse is going to be 0. The biggest one would be 4, and hopefully that makes sense, that assuming they all have the same mass, they're going the same speed, they would all exert the same force on that stick, which then means, well, torque is force times lever arm. Force times lever arm, and 4 would have the biggest lever arm. So 4 is going to be the winner. And then it comes down to 1 and 3. Well, remember, okay, perpendicular. So if I was to look at the components, this component is smaller than this component. So even though 1 and 3 have the same R, 1 has a smaller force because there's a smaller component that's, applying the force that's going to cause the torque. So 1 is the loser, so it would look something like that. Why do we do this? Okay, here's why we did this. Well, you can see all of these things are moving straight. They have linear momentum. But 3 out of those 5 things caused this thing to rotate. So afterwards, if it's stuck, and it's a blob of clay, so it would, if it's stuck, then you know what? 1, 3, and 4, beforehand, your system has angular momentum. Therefore, afterwards, your system has angular momentum. So let's talk a little bit more about that. So first of all, an object moving in a straight line could have angular momentum depending on the axis of rotation. So, an object moving straight could have angular momentum depending on the axis of rotation. Okay? So here's what I mean. Just like we just kind of talked about. If I have an object moving this way, and that's the axis of rotation, let's try that again. That's the axis of rotation. That object would have no angular momentum. Okay? That's not going to cause a torque. It doesn't really matter what the shape is. If I put some random shape there, it's not going to cause a torque. But if I have an object here and my axis there, that would have angular momentum. Okay? Why? Because, hey, look, there's my random shape. If you see, it's going to hit it, it's going to cause it to rotate. So as long as the object is not moving straight at the axis of rotation, okay, it could supply a torque to an object. Therefore, this object has angular momentum. All right? So now let's talk about how do we find how big that angular momentum is. All righty. All right. So let's say you have a problem like this. Let's go back to our setup here. And you have this thing moving like this. And then afterwards, this is what your system is going to look like. So this thing's smushed on here, and then it's going to cause it to rotate. Okay? So if you were to set this up, and you'd go, all right, well, we already know that this has angular momentum. Because, hey, it's going to cause a torque, so therefore it's going to have some angular momentum. How do I determine its angular momentum? That's what we want to talk about. I think it's a little bit easier, remember, when we're doing conservation of momentum or angular momentum, especially if you're setting up an experiment, you want to set it up right before and right after the collision. So let's look at this right before the collision. So rather than right here, we're going to look at this immediately before the collision. So immediately before the collision, this thing is right there. It hasn't quite hit it yet. And it's moving up, okay? So this little ball is moving up like that, okay? This stick is not moving. So if I want to write my equation, I would say 0 for the stick plus I for the ball, or we'll call it the clay. So clay, omega for the clay equals, over here I have I for the stick plus I for the clay times my new omega. So I'll call this like omega 1 and omega 2. Okay? Just like when we were doing our other equations. Picture, use your picture, write your equation. Now you have to determine, well, how do I find I? Well, if you look, do you see how this ball, all of its mass is a distance r away? Well, if all of its mass is a distance r away, you can treat it like a point mass, which means this would be mr squared. This would be the mass of the clay. And then this, well, hey, this is moving in a straight line. So how do I get omega in terms of v? Well, you draw a circle. You say d equals 2 pi r. Theta equals 2 pi. You relate them. And then you say, oh, if I would say d divided by t, I get v. If I get theta divided by t, I get omega. And then omega equals v divided by r. So if I plug that in, v divided by r, and then this you would have to know whatever that is of the stick plus this would be the same, and then you could solve for this. So if you look, and yeah, you could do a little math here, this could cancel that out. But if you look, as long as I know this, this, and this, and I know this, this, and this, I could easily solve for that. Object moving in a straight line has angular momentum. Bye, kids!